Okay, so let's talk about the actual observation made by the pulsar timing arrays. So in 2020 and also 2021, there were press releases from the different pulsar timing arrays, right? So different pulsar timing arrays are the Parkes pulsar timing array, located in Australia. There's the European pulsar timing array. There's Nanograph, which is the US version. And now there's also the Chinese pulsar timing array. So they were not part of the 2020 release, but then they were part of the 2023 release. So in 2020, I mean, this is not the first data release, right? I mean, people have been doing this for a long time, right? And they've been putting bounds, and bounds, and bounds, and bounds. And now 2020, instead of putting a bound, they said, we have discovered a common stochastic process. Right, which means they saw in their data an additional noise source, which they could not explain with the noise models that they had for the pulsars, with the timing models that they had for the pulsars, and which seems stochastic and which was common across all pulsars. Okay, so it's not something in a single pulsar, but it's really kind of an additional noise source in all pulsars. So the way they show this is they show the time delay. So this is log 10 of the time delay in units of seconds. And here's the frequency in nanohertz. And okay, at high frequency, about above 10 nanohertz, they know that they have a lot of noise. So this is kind of the noise of the pulsars, right? So all measurements are consistent with a 0 time delay. But then at low frequencies, right, so down to about 3 nanohertz, which is the inverse of 10 years, they say, okay, we saw something, right? Maybe like this. And so we say, okay, this is consistent with saying, okay, there's something here which we can fit with the power law, because we can fit everything with the power law if the data is poor. And we say, okay, this is noise dominated. So we don't care, we don't know, we cannot get any information here. But here we see something which is an excess over what we expected. And hence we expect that this here, this is something new, right? So at this point, they've not yet seen the Helling-Downs correlation, right? There was not enough statistics to see the Helling-Downs correlation. But they say, okay, we see something. We don't know what it is, right? But it's excess noise, and excess noise is exactly how you expect a stochastic background to show up initially when you don't have enough data to make a conclusive detection. So you can fit, okay, as I said, you can always fit a power law, right? So you can do a power law fit. And we're going to parameterize our power law by some amplitude at some reference frequency, which, okay, fref, f over fref, and t. Okay, that's just a parameterization of the power law. You can do it. I mean, you can do it for omega. You can do it for the time delay. You can do it for the redshift, right? Depending on what you do it for, you will get a different index here, but they are just related to each other by, okay, keeping track of which observable you're actually looking at. So let me draw. So then I can draw a plot of this amplitude as a function of the tilt and t. And I'm going to do this now for reference frequency, which is the peak sensitivity of PTAs, right? So I'm going to do this for reference frequency of 3 nanohertz, right? So 1 over 10 years. So this is 1 over 10 year. And if I do that, I find for the posteriors of my power law fit that the tilt can be anywhere from -1 to 3. But the amplitude is pretty good constrained between 10 to -9 and 10 to -10. I should give you units here also, right? So this is microseconds. That goes down to about 10 to -8, right? So this is just, remember the pulsar signals themselves were milliseconds, right? So in a millisecond signal, you're looking for a microsecond deviation. Okay, so I do the fit. I get this ellipse, right? Which kind of tells me, okay, the best fit power law has an amplitude around 10 to -9, 10 to -10 in omega. And the tilt, to be honest, -1 and 3, right? I mean, to be honest, the tilt can be pretty much anything. You may have seen this plot in a different way. You may have seen this plot, and it looked like this. Okay, you may have seen this plot and said, they see a correlation between amplitude and tilt, right? So that has information that tells me something. This ellipse comes from saying that the reference frequency is 1 over year. I can do that, right? I mean, I can reparameterize my power law by taking a different reference frequency. It's mathematically correct. It's kind of convenient because, you know, when people started doing that, they only had order a year of data, and then why change your convention? But the correlation that you see is entirely due to picking a reference frequency, which has nothing to do with the sensitivity of your instrument. Okay, so there's no correlation. As expected, we have a measurement of the amplitude. We have essentially no measurement of the tilt. It hasn't changed much. You mean, no, it's I mean, well, and so the fact that the ellipsis is crooked, yes, it's crooked if you take this reference frequency. If that's what they do, there's nothing wrong with that. But there's still no, that doesn't mean that there's any information on the tilt. There's no, no, it doesn't matter. When you do the fit, it doesn't matter, right? I mean, this formula is mathematically correct for whatever reference frequency, right? Just the thing that I'm plotting on the axis is not the amplitude of the PTA frequency. It's just the amplitude of a different frequency, right? So what I'm doing is I'm saying, okay, here's my PTA thing, right? I want to parameterize this by a power law. Well, what would you do, right? You would take the reference frequency here, right? So that you have amplitude and tilt at this point. You can take the reference frequency here, right? The tilt will be the same. The amplitude will be different, right? So yes, you will get a different amplitude. The amplitude will depend very much on the fit, on kind of the tilt that you did, right? But it's completely artificial. It's because you're parameterizing your signal by a tilt and an amplitude, which is outside, which is not where your detector is particularly sensitive. So it's correct, right? It's not saying it's not correct, right? It's mathematically absolutely correct. It's just, if you then go back and say, aha, the thing that I saw on the axis is actually the amplitude here, that's wrong. So it's a matter of convention, but people get very confused about it and build very complicated models that correlate their amplitude and their tilt in a very complicated way. Don't, okay? We have a measurement of the amplitude. The tilt is, I mean, unless you have a really crazy model, which has an incredibly steep spectrum, you're going to be compatible with the data at the moment. Okay, so then 2023, last year, Then now the statement is really, we've seen the Helling-Downs correlation, right? So we've seen the thing that is really a smoking gun signal of the gravitational wave. So this is essentially already the plot that I drew up here, right? So we saw something, we measured S alpha, S beta as a function of gamma, and we saw something like this. Oops, the other way around. Something like this, with some big error bars. The significance is about, and they all see it. They all see it with different evidence, right? And then a bit depends on how conservative you are and the claims that you make in the abstract. So they see it between 2 and 4 sigma, right? So let's say, I mean, roughly it's at this point maybe a 3 sigma-ish detection, 3.5 sigma. If you cannot, at the moment, you can, I mean, okay, you can take the ellipses, right? Of course, I have a Mathematica notebook, right? You can take the different ellipses and you can overlap them, right? And you can kind of see, okay, more or less they agree, right? So they're all kind of more or less getting the same amplitude. They don't completely agree on the tilt, right? But then again, I mean, the tilt is just, I mean, they definitely overlap, right? So some are maybe a bit more on this side, some are a bit more on that side. But roughly this is the picture. And again, the tilt is still so uncertain, right? It tilt also depends very much on kind of, you know, is this bin still measuring signal or is it measuring noise, right? And then here there's one bin which is a bit up, right? Is that signal, is that noise, right? So the tilt is just not known yet. But they basically all see the Helling-Downs correlation between 2 and 3 point something sigma. And eventually, they will combine the data. It's not completely trivial to combine the data properly, right? Because you have some pulsars which are common in both data sets. You can have some telescopes which are common in both data sets, right? So you have to not double count things. And they also use different noise models for the pulsars. They use different analysis methods, right? So it's the collaborations will get together, right? They have this international pulsar timing array collaboration where all the different pulsar timing array collaborations, apart from the Chinese group, are inside, right? And they will, you know, sit down, and they have also in the past put out common data releases. They're usually a couple of years behind the individual data releases because doing this exercise does take time. But they will get there, right? And I mean, kind of the hope is that now there's more pressure to do it, right? So maybe in a year or so, right? I think it would be not unrealistic to expect something. And then it would be not unrealistic to really expect enough significance to get to 5 sigma here. There was a question somewhere? Yeah. Yeah.
I heard that, for example, ETA doesn't have such a sharp detection of the stochastic signal. So I remember you were saying that for diamond stochastic or non-stochastic was 50-50. Is this the case still, or now we're converging on stochastic signal?
So you mean stochastic versus noise or stochastic versus plane wave?
Stochastic versus plane wave.
Both data sets are completely compatible with plane wave. Yeah, this is the exercise we did here, right? It's mathematically the same integral.
Plane wave, I mean source. Sorry, not plane wave.
Like a binary and spiral. Yeah. Yes, that is basically a plane wave.
Yeah, but constant direction.
Yes, you do. This is exactly the computation that we just did before the break, right? You can either average, for the stochastic background, you say the background is isotropic, you do the sky average for that reason. For the plane wave, you say I have many pulsars, and I do the sky average because my instrument is isotropic. In the limit that you have infinitely many pulsars, it's mathematically the same integral. Now, we don't have infinitely many pulsars, right? So there is a small difference, but within these error bars, you cannot tell the difference. So both data sets, I think, are completely compatible with.
Why people believe that with stochastic signal instead of the source?
I don't know who is people, right? I don't. So I think one has to distinguish the press release from the papers. Okay, and I'll get to that. I'll get to that, right? That's a different story, right? That's the question. We'll get to that in a second. How well the astrophysical expectation, given what we know about black holes, matches the data, right? That's a different story. Here we're just saying, can I distinguish a plane wave from a stochastic background, right? Where I kind of have no constraints on the amplitude of my plane wave. And there I cannot with the current data, at least not to good significance. Right. So exactly so this is what we've seen, right? So the questions: is this a classic gravitational wave background or a single source? At the moment, right? We don't know.
If it was a stochastic gravitational wave vector, so it would be made anyway by sources. So how many sources should I take?
I'm getting there. So now here I'm distinguishing, stochastic gravitational wave background, kind of isotropic to the point that we have current limits on isotropy, which is very poor, right? Or a single source. What's the best way of distinguishing this, right? The best way of distinguishing this is looking at signal per frequency bin. Because the single source will just be sitting in one frequency, right? Whereas, so if I go to this picture for the Hellings Downs, I say is the same, right? But this picture is not the same, right? Because for a single source, the signal is really driven by a single frequency, right? So I really expect to see the signal driven here by a single frequency. Whereas with a stochastic background, I really expect, depending on the shape of the stochastic background, right, I expect the signal to be in many bins. Now, they have an analysis like that, right? They look at evidence both for this and evidence, in particular evidence of the Hellings Down per frequency, right? To see, okay, do I actually, if I bin my data per frequency and I redo the analysis, which frequency bin is driving my evidence for Hellings Downs? Now, the issue is, since I only have about 3 sigma significance, if I take everything together, as soon as I chop my data into smaller bits, we're talking about 1 sigma fluctuations up and down, right? So it's just not enough data. But again, combination, right? Combination of data is the key. Because we're looking at cross correlations, right? Sure, more years helps because you gain with square root of time. What helps even more is more pulsars, right? Because what counts here is pairs of pulsars. So as you combine, as you add more pulsars to your data, you start observing more pulsars. Also, you combine different data sets which contain more pulsars. The number of pulsar pairs grows as n squared, right? So you really gain. So we don't have to wait another 100 years, right, to get significantly more statistics, right? We need to combine the data, and we need to get more pulsars. And there are a ton of more pulsars in the sky, right? The question is identifying the clean pulsars and getting observation time on telescopes to observe pulsars, right? But nanograph, for example, is like really upping the number of pulsars basically by the year. So the way to go is evidence by frequency. You can also try and go by anisotropy, right? But anisotropy is much harder because you really need to kind of measure it down to a certain level, and B, you have this issue of cosmic variance, right? So anisotropy is harder. However, if we do this measurement, right, and we convince ourselves that actually the thing that we're seeing is extended over many frequency bins, right, then we know it's not a single source, right? But it could still be a stochastic background of cosmological origin, right, which is essentially isotropic, or it could be a stochastic background of different sources, right, which is roughly isotropic, but not quite isotropic, right, because it will be dominated, and that was your question, it will be dominated by a few nearby sources, right? So this is the question: cosmological versus astral. right? And this question is really only a question, right, if the answer here is this one, right? Otherwise we're done. And the way to do that is to measure anisotropy. So that's the next step. So how do you measure anisotropy? So what you do is you go back to this formula, right? But you don't make the assumption of isotropic. You probably still want to make the assumption of unpolarized, which means you leave this P of k inside the d3k integral. Okay, and now you do a multipole expansion. Okay, so you leave this P3k inside here, and then what this becomes schematically as alpha as beta. So we can take the sum of polarizations outside. Well, we can leave it inside, sorry. We do the, well, we can take it outside, doesn't matter. Sum of a lambda integral over d3k. And now you do a sum over multipoles, right? And you basically have multipoles in your power spectrum, and you have multipoles in your response function. So f lambda k alpha f star lambda L beta k hat. Okay, don't take this too literally, right? This is to give you the idea, right? You do the same, something similar to the CMB, right? You do a multipole expansion of the response function and a multipole expansion of your background, and now there will be some coefficients here, right? Some CLs, and you will, well, CLs they are in here, right? Describing kind of how much power do I have in which multipole. And now I can put bounds on my CLs, just as in the CMB, from the fact that this observation deviates from that prediction. Okay, so the prediction for isotropic is Helling's downs. If I drop the assumption of isotropy, I will get some deviations from Helling's downs. But now the issue is, well, A, my error band has data, my data has error bands. B, I have cosmic variance, right? So it's not a completely trivial measurement to do. However, we do already have bounds. So the current statement from nanograph in particular is that the higher multipoles, so everything apart from the zero multipole, which would be the isotropic background, cannot be larger from current data than about 10%, well, let me say 20%, right? But something on the 10%-ish order for L smaller than 6. Okay, so you're not going to expect measurements of very high multiples because your response function is very, very broad. But you can put already limits on some of the multipoles, and they're at the 10-20%-ish order. And that is, in fact, the same, roughly also where you expect the astrophysical background to be anisotropic, right? So if the signal is due to kind of a bunch of supermassive black hole mergers, you will expect that this thing is driven by a few close-by sources. And then depending on the details of your galaxy population model, right, you expect anisotropies at the 10%-ish level. Okay, so this is something we can get at, right? This is something that not in the not too far future, maybe even in the combined data release with the current data, they can get down to the level that you could actually make a conclusive statement on astrophysical versus cosmological. Yes, next topic. That's basically the astrophysical source that people are thinking about. So very good. You nearly don't need me to give this lecture. supermassive black hole binary signal. Okay, so this is the leading explanation for an astrophysical signal, right? And it's probably the leading explanation for any signal because life is always astrophysics. So what is this, right? So this is the superposition. So the supermassive black holes, right? These are the black holes in the center of galaxies. So when we're talking about a supermassive black hole binary, we're talking about two galaxies, think two Milky Ways, which are rotating and eventually colliding. So even if it's just astrophysics, right, it's still very exciting. So what we will be looking at will be the superposition of many or several supermassive black hole binary signals. We may also just, as I said, we may also just be seeing one, right, if it's sufficiently close. But then this then goes into the question of doing a frequency analysis, right? So under the assumption that it actually is a stochastic background, right, let's understand the properties of this leading astrophysical candidate. So to compute the gravitational wave background from this, right, so the energy density, we know we can parameterize with the omega, which is just the spectral density of the energy. So that's just rewriting the formula we've had a couple of times. Now, let me consider these signals, right? So I will need to do an integral over frequency, because these black holes are emitting at different frequencies. I need to do an integral over redshift. I need to count the number of galaxies that I have at a given redshift, or more precisely, the number of binaries that I have at a given redshift. I need to, the frequency that is emitted, I will need to redshift it until today. And then I just count, right? But I need the energy, right? Because at the end of what I'm computing here, I'm computing the energy. So basically, all that I need to do is here dE, the energy, right? Then I would be more or less done. But I'm going to rewrite this as dE, dln f, dz. Okay, so integrating over frequency, integrating over redshift. And this here is why I, at the very beginning of the lecture, reminded you that the energy scales as frequency to the 2/3, right? That's just an orbit of 2 point-like particles which are which are circling each other. And so if you're losing energy only due to gravitational waves and nothing else, right, as we discussed in lecture 2, right, then you will get here that f, well, dE over dln f, right, is f to the 2/3, okay? Because you take a derivative, right, but then you have ln f, right? So you lose a power, you add a power, and you get back to the same scaling. Which means that this guy, right, now I equate this with this, right? So the dln f integral just stays on the outside. I need to perform the z integral, but I will obtain that omega gw should scale as f to the 2/3. This is assuming, it is making some implicit assumption here about the number of events, right, that they are kind of somewhat isotropically distributed in redshift up to a certain redshift. But what I expect is omega to go as f to the 2/3. And this thing, this 2/3, right, is what we called NT. Okay, so now you can kind of go here, right, and see how well this fits into here, okay? And what you see is that, okay, so this data is a bit my kind of subjective average over well, or my average over the different collaborations, right? So actually this data is, there's some which are a bit more over here, right? And there's some which are a bit more over here. Nanograph is a bit more over here. The 2/3 is about here, right? So this is 2/3, right? So perfectly consistent with some of the experiments, and not with nanograph, it's on the edge. But, and this is what you were referring to, right? That they basically say, okay, well, in the main paper, they say, okay, this is the expectation, and this is my data, and there's a like 2 sigma tension between this expectation and this data. But given that different experiments, right, measure a broader spread, and they have to be measuring the same thing, right? I think the last word on the data has not been said yet. And there's also a caveat on the theory. Where did I put it? Maybe here. Okay, so this value is a bit small compared to the best fit value of nanograph. So let me. So if I just do nanograph, omega nt, then I will get, okay, here is my 2/3, right? And my data is kind of here a bit, right? So I'm like, well, not even, I mean, it kind of touches, it's really like this. Okay, so I'm like, maybe is this an indication this is not the right explanation, but, so the other data is more on the left, right? So there's two reasons why actually you shouldn't expect this tilt from the theory side. One is that at low frequencies, right? So on the left of that plot, maybe we should draw that plot again, right? So, well, actually, this is not omega, but this is delta t, right, over f, right? So this is the prediction that we just derived here. But one thing we assumed is that we have purely gravitational energy loss. We know that is incorrect because this is the whole conundrum around the last parsec problem. Yeah, the two black holes, they need to get sufficiently close, and once they're sufficiently close, then indeed, you know, they can lose energy purely to gravitational waves, and that will lead for them eventually to merge. However, when they're too far apart, right, it would take forever, longer than the lifetime of the universe, for them to actually get together. Now, we kind of do know that these black holes do merge, right, because we see galaxies where this merger has happened, right, or we see galaxies where the merger has happened in the past. They just look like they've just crashed into each other. So we know that galaxies do merge, but there needs to be some mechanism which kind of initially gets the black holes close enough together, right? So this is some additional mechanism. It doesn't have to be new physics, right? It's just, you know, standard model astrophysics, complicated stuff. There's not just two black holes. There's a whole galaxy attached to it, right? There's stuff going on. And this stuff that is going on will lead to additional friction and energy loss into things other than gravitational waves. And that will be has to be important when the black holes are still a bit apart, which is low frequency. And so we expect typically some turnover here. And how exactly that turnover looks like depends on astrophysics, right? Depends on your model for galaxy population, disk properties, things we don't fully understand. So at low frequency, other energy loss mechanisms. The other thing that you expect is that here we've implicitly assumed here that we basically have, you know, enough. We've assumed here that in every frequency bin, we've have enough integrals that we can sensibly perform a redshift integral. Now, as the black holes go closer together, we know the signal chirps, right? So the frequency increases faster and faster and faster as the black holes go together, which means, say you have an isotropic distribution of black holes with an isotropic distribution of distance in the universe, okay? At low frequencies, you'll very easily find a black hole at that frequency because, you know, they stay at that frequency for very long. As they go closer together, they start going through the frequency band very, very quickly. So they only stay a short amount of time at any given frequency. So if I'm now saying, aha, but I'm looking for black holes at these frequencies, right? They're going to be unlikely to find because every single binary spends very little time in each frequency bin. So if I have few binaries here, I don't actually have a stochastic background, right? I just have individual sources. So what I expect at high frequencies is not actually a stochastic background, but, you know, just some stuff, data, right? But no longer a proper stochastic background. So at high frequencies, low F, high F, few events per frequency bin. So this means that this line was too optimistic, too simplistic, and now you can kind of do different types of modeling, right? Depending on how well you think you understand astrophysics, right? So, and in the nanograph paper, they present two models, right? One, so this is the data, right? And then they have one model, which is like this, right? And they say, aha, maybe there's here some tension. They also have another model, which is like this, right? Other model, right? And there's no more problems, right? Now this model, okay, maybe I'm slightly overdoing it, right? I think there is, but really not by much, right? I mean, it is like kind of, well, okay, it doesn't go negative, right? Okay, well, whatever, you get the idea, right? This model is maybe not really what we would call a model, right? Because it's more what they call a phenomenological model, right? So which means I kind of have a bunch of effective parameters and I just kind of can vary them very freely. But this is just to say kind of there's enough astrophysical uncertainty in the modeling that at the moment I don't think we can very conclusively say that there's a problem with the astrophysical signal. Within the astrophysical uncertainties, it still seems, within the astrophysical uncertainties and within the data uncertainties, it's still a very plausible explanation. And so the way to distinguish this is, I think, not the tilt, right? Because we have no prediction for the, we have no measurement of the tilt from the data side, and we have no prediction of the tilt from the model side. So the way I think to go is not the tilt, at least not in the immediate future. Eventually, yes, right? Eventually we'll get better measurements of the tilt. But I think the way to go is to look at the evidence per frequency bin and the anisotropy, and that will allow to distinguish. I hope, unless after the fact they change the model again, right? Which is always a possibility. Okay, any questions on pulsar timing arrays?
As you mentioned, that higher frequencies, we do expect to see particular events of burning supermassive black holes. Were there any attempts of using it to monitor one particular spiral of supermassive black holes? Because I guess without observations, we do know maybe where to expect where to find
So I don't think that there's any verification binaries for pulsar timing arrays as there are for LISA, right? So for LISA, we'll get that in a second. For LISA, you kind of know some known signals because you've seen them in the optical range, right? So you know you really should see them. I don't think so for pulsar timing arrays. I don't think that there's, I'm not aware of kind of a single event that we kind of know we should see something from that. The issue also at high frequency is that you are noise dominated, right? So it's also not completely easy. But I think the goal is more statistics. More statistics, I think, will answer these questions.
From an actual point of view, is there some idea on how to solve the final Parsec problem for such huge black holes?
I'm not an expert. I've been told yes, right? So I've been told that the environmental effects within the uncertainties, well, basically within these uncertainties, right, can take care of that.
I mean, it's just a power law parameterization, but there is no reason why it shouldn't be.
What do you mean?
About the environmental effect.
No. There is a reason, right? Because the environmental effect. Well, I mean, so the logic is, I mean, you have the entire disk attack. I mean, the last Parsec problem comes if you kind of think of the black holes really as point-like particles, right? And then you ask, how long does it take, you know, to get all the way to the merger? You find out this is longer than the lifetime of the universe, right? But then, I mean, you also have friction from the collision of the disks, right? But, I mean, there's a reason people thought there was a problem, right? And obviously people knew that there was a disk. I'm not an expert, okay? I can't tell you exactly what is the status from the astrophysical point of view. Might also depend on who you ask. Okay, let's briefly in the last 10 minutes talk about LISA. Okay, so LISA is a triangle, or will be a triangle. Let's call this X, Y, and Z. And you can here artificially construct, because, I mean, okay, initially the problem is you just have one detector, right? How on earth are you going to measure cosmological background, right? How are you going to measure anything, right, if you kind of can't cross-correlate two different detectors? An Einstein telescope is a similar configuration. So the trick here is that it is a triangle, and so we have three interferometers, right? So this X interferometer is between these two satellites. The Y interferometer is between these two satellites. And then the Z interferometer is between these two satellites. Okay, so you have three interferometers in one. However, they are, of course, correlated. Yeah, they share common links. They share common nodes. So you can take the response of these three interferometers and ask, okay, can I construct independent interferometers, right? So I basically want to take, not physically, but kind of afterwards, linear combinations of the outputs of these interferometers to obtain interferometers which are orthogonal, right? So they are as independent as possible. And so this leads to the orthogonal, or approximately orthogonal, so-called AET channels, which are linear combination of these X, Y, and Z channels. So SA, for example, is 1/3 2SX minus SY minus SZ. SE is 1/3 SZ minus SY. And ST is 1/3 SX plus SY plus SZ. This ST is often what people refer to as the null channel, because it is actually pretty much insensitive to signal, but it is pretty sensitive to noise, right? So this is a good way to measure your noise. And these are essentially the two signal channels, which are orthogonal, which is kind of good for the noise in the sense that if you cross-correlate them, your noise is basically uncorrelated. Unfortunately, they're also orthogonal for the signal. So if you cross-correlate them, your signal is also gone, right? So you cannot, at leading order, you cannot work with cross-correlations in LISA. You can only work with autocorrelations. So NAE is 0, right? But SAE is also 0. So what you have at your disposal is signal channels, right? SAA, right? Which will be, this will contain signal plus noise. And then you have STT, which will be driven by noise, right? And that's how you want to distinguish signal and noise with LISA. You can, at leading order, you cannot do cross correlations. There's another trick in LISA, right, which kind of complicates a bit the initial picture. And that is that actually you have a huge laser phase noise that you have to suppress, otherwise you could not measure a thing. And so actually, it's not just the X interferometer, right, is not just sending a photon here and back and sending a photon here and back, but actually it is what is called time-delayed interferometry, which is that this X channel actually implies that you have to send the photon here, back, then over here, back, then you arrive back at the origin, and you take the other photon and you send it the other way. So you send it here, back, right? And only here at the end do you do the interferometry. Okay, so each photon, right? But I mean, yeah, you phase couple the laser, but conceptually each photon has to go all the way around one arm and all the way around the other arm. And the reason is that then by doing it this way, you ensure that two photons which are emitted at the same time here, once they've done with their trajectory, if there's no gravitational wave, they will actually arrive back here at the same time, right? If you don't do that, that would only work if these two arms had exactly the same length, right? But exactly to the same length to the degree of a wavelength, right? And you cannot put two satellites in space 2.5 million kilometers apart and have them at the same position up to a nanometer, right? That's just impossible, right? So the arms will kind of, yes, they'll both be 2.5 million kilometers, right? But not exact to the nanometer. And to compensate for that, you work with these TDI variables. And then you can do even more complicated things, right? So this is called first generation TDI. Then you can go to higher generation, where you do even more combinations of where you're sending the photon, right? This is kind of done virtually, right? This is not done physically, right? But these are then the measurements that actually happen in LISA. So this is, cancels laser phase noise for unequal arms. But it still assumes the arms to be static, right? But the arms will also not be perfectly static because the satellites will be wobbling around a bit, right? And then you can do another round of going around the instrument, and then you can, to some extent, also cancel the noise, the laser phase noise, for not static arms. The expected, okay, so that's basically, I think that's what you should know about the instrument, right? I mean, kind of everybody knows it's a triangle, right? But I think this is, like you should know in LIGO, right, that there is a cavity, right, and the photons bounce back and forth, otherwise you're going to get very confused about why is it sensitive at this frequency. I think this is what you should know roughly about LISA to understand the types of measurements that you can make. Now the signals we expect in LISA right, so this is known signals, astrophysical signals, right? Like the black holes in LIGO, like the supermassive black hole binaries at PTA. So we expect, again, supermassive black hole binaries. So with higher frequencies than pulsar timing arrays, right? So pulsar timing arrays see the in spiral when the black holes are still a while apart, and kind of they're just going around in circles. In LISA, we expect to see the mergers. So the same black holes we see at PTA, millions of years later, right, they will be in the LISA band. We also expect to see galactic, so these are extragalactic, right, because these are merging galaxies. So we expect to see galactic, stellar origin, black hole binaries. So the key to know about LISA is they love acronyms, okay? And here, these are the guys we see in LIGO, right? 10 solar masses. And in LIGO, we see the merger. Here, with lower frequencies, we see the in spiral. So we would see these guys at LISA months, years before we see them in LIGO or before we see them in the Einstein telescope. And in principle, we can measure enough oscillations in LISA of this that we can get an accurate measurement and really predict the waveform all the way to LIGO. So you could say, hello, my friends from LIGO, 5 years from now, on January 1st, whatever year that is, at 0.00, you're going to get a signal, and the phase is going to be pi over 0.3. And that's an incredibly sensitive measurement, right, if something went wrong in the meantime. In principle, right? Then we in a second we get to the practical problem. And the other thing we expect to see is galactic white dwarf binaries. These are the verification binaries, right? So these are white dwarfs which we know are there in the galaxy. We know they're binaries. We've seen them in the optical range. We've even already seen them, we've seen them in the optical range. And so some of them, so we expect that we're going to see them in the gravitational regime with LISA. Now, the challenge is we don't only have a few of them, right? In LIGO, we see an event, and then, if we're lucky, the next day, the next week, we see another event, right? The event lasts seconds, okay? So most of the time, LIGO sees nothing. And we can use that to calibrate our instrument, to understand the noise, to do tests, all these things. In LISA, we expect to see thousands of signals, several thousands of signals, and those are only the ones with a signal which are loud, with a signal-to-noise ratio of much bigger than 1, right? So it'll just be a mess, right? It will be like the LHC, right? It will be like tons of overlapping signals going on, and these signals last a long time, right? I mean, these can last the entire mission duration. So you expect thousands of overlapping signals going on in your detector. You have no way to shield the signal. You have no way of, actually getting this T channel is to some extent a null channel, but it's not a very clean null channel, right? So you have no way of really turning everything off and measuring your noise. Sure, you can measure your noise on the ground, right? But then you send the satellite up into space and all sorts of things can go wrong. So we expect this. On top of that, we expect a stochastic background astrophysical, right, from unresolved sources, just call astro, right? Because if we have tons of events which we can observe, there'll also be even more tons of events that we cannot observe, right? So we'll also have significant background from astrophysical sources. And on top of that, we want to detect our cosmological stochastic background, right? So when people say, aha, sensitivity of LISA, my model, right, I can detect, they ignore this entire problem. And this is a problem which people are working on, right? Okay, we don't have to solve it tomorrow, right, because we don't have LISA yet. But we will have to solve it, right? Because at the moment, your model Not even close, right? So let me just say, and this is a good point to finish, data analysis channel, right? So there's the way we think about data analysis, the way we do data analysis is just going to be completely different for LISA, and similarly for the Einstein telescope, than it is with current gravitational wave detectors, right? It's like going from, you know, the first generation of particle physics colliders to the LHC. You have completely different types of problems that you need to solve, and you need people, young people, to think about them and come up with brilliant solutions. Okay, and with that, questions? Okay, I saw a question there.
Do you think that the background data removing techniques from LHC, you know, that expertise could be easily transferred to this case or not? Like machine learning approach that in the last year are quite
Yes, so easily, I think nothing is easy, right? But yes, so one of the things that I'm working on, for example, despite I have no clue about machine learning, but I have collaborators who know about machine learning, is to think about machine learning approaches for this problem. So I think a lot of the, I would suspect kind of a lot of the ideas, the philosophy can probably be transferred, but then of course in practice, the exact thing you do is going to be different.
So regarding this difficulty of processing data, how much of it, I mean, up to what extent is precise modeling of the signals important? I mean, I guess that's not the only issue, but how relevant?
Okay, so,
Considering the other.
right. So I would say for the transient signals, right? So for the waveforms of the black hole binaries and stuff like that, it's very important, right? Because if you have a ton of stuff going on here, right? All these events, right? I mean, the only way you can hope to do this is that, you know, you do a multi-parameter fit, right? To all the signals you have in the data, right? But for that, you need to parameterize them properly. You need to really understand well your signal, right? Because if you're, so this, if you do it naively, right, you say, okay, I'm just going to, I have my data, I have all my possible signals, right? I'm just going to try and fit them all at the same time. I mean, the problem is that you have something like 10 to the 6 parameters or so, right? So you fail if you do it just brute force. But in principle, you want to do a smarter way of that, right? So you want to kind of fit all the possible signals and all your at the same time. But now, if you have misunderstood what exactly your signal looks like, right? If you want to kind of fit this and then you subtract it from the data. But if you kind of subtract it wrong, right, because your waveform was incorrect, you're going to be left with residuals, right? And that's going to then destroy your capabilities of measuring something below here, right? So for the waveforms, I think is absolutely crucial, right? That these are known to the necessary precision. Now for stochastic models, right, like this thing down here, it's a bit of a two-edged sword, right? So on the one thing, I would say, okay, there's two separate challenges, right? And I think kind of we need people working on both of them, right? So if we don't manage to resolve this data analysis challenge, right, it doesn't matter if this looks like this or even a bit different, right? If you had a model where you don't have any free parameters, right, or very few free parameters, and you can really tell me this is exactly the signal I expect and nothing else, right? Because whatever, in order for my model, I don't know, to give me primordial black holes, which are all the dark matter in the universe, right? I know all my parameters, right? And I know exactly what I'm looking for, right? If you know that, then it's very useful, right? Because then I can go into my data analysis and I can really use that as a template. But if you tell me, okay, I know exactly what is my shape, but I have 10 free parameters in my model, and as I vary these 10 free parameters, I can get basically everything, right? Then that's not helpful for me in order to do this data analysis challenge. But that said, if we manage to do this data analysis challenge, right, if we manage to solve all the other problems in here, right, if everybody else managed to do kind of precise estimations of their signals, right, then we will be able to reconstruct some residual background, right, similar to what was done in PTAs. And then it will be extremely useful if you kind of then already know how to relate that to your model, right? Because it's a lot more credible if you have the model before the data, rather than you get the data and then you kind of fix your model to fit the data. So I think both is important. And I think they're just two separate things that we need to do as theorists, right? We need to kind of solve this data analysis problem, but we also need to make sure our models are ready, because I don't want, I mean, I'm afraid it will, but I don't want that this was what happened with the supermassive black hole mergers happens to us, right? Where you kind of tell people you have a prediction, or, well, okay, maybe we're just not reading the right papers, right? But somehow we thought there was a prediction, right? Then there was the data didn't match the prediction, and then you say, oh, well, actually, our prediction is like this, right? It's always like that, right? But the more you can anticipate that, right? I think the better you're prepared, the more credible you can sell your model. Okay, so I mean, there's two things, right? So one is mock data, say for LISA, right? So there are these LISA data challenges, right? So there's a team within LISA that regularly publishes these LISA data challenges, and the old ones are still public, right? So one can go and try. So they give you basically, they have a big simulator. They generate mock data, right? So they simulate the entire instrument, they simulate the data. They build up in difficulty, right? So you will first get some data which is just noise and a few signals, right? And then they add more and more signals, right? And your task, they don't tell you, they tell you what classes of signals are inside, but they don't tell you exactly what signal is inside, right? And your task is to take this thing that they give you, this data, and try and find the signals in the data, right? So that is kind of something which is out there, and which they're always looking for people to participate, right? And to come up with new ideas how to do the data analysis. Now, the other question is, you know, given I have a model, right, how good is the prediction for the stochastic background? That depends very much on the model, right? In some models, it's very simple to get the correct answer. In other models, it's much more difficult. I mean, I mean, with this, I mean, there will be an astro stochastic background, right? Just simply because we have a bunch of resolved sources, right? And we will have a bunch of unresolved sources, right? And these astro backgrounds are known to the degree that you have trust in population models. Okay, so, I mean, here, like, for example, I don't know, take, okay, so this one, you're in the merger phase, right? So you're not so concerned about stochastic background, right? So the most important for the stochastic background are these two. So if this is, again, our LISA curve, right? So this is our sensitivity curve, just noise instrument response, right? And we have not yet talked about any other signals. The unresolved galactic white dwarf binaries give you a bump here. Okay, so that's what you expect to see. Also, because they're in the galaxy, it's not going to be perfectly isotropic, right? So if you're not going to confuse this signal with a cosmological signal, right? Of course, if your cosmological signal is way below this, right, you're still screwed, right? But you're not going to confuse it because it has a different structure in space. Same for these guys, right? They're largely the galaxy, though there are also some extragalactic ones, right? So that's a bit more difficult. And here we're really deep inside the inspiral, right? So here this derivation that we did earlier with the f to the 2/3 applies, right? So you're going to expect something here like this, That scales as f to the 2/3, right? Because you really are in the spiral. You don't have to worry about additional energy loss. You don't have to worry about, well, you might have to worry about if it's actually purely stochastic or if you have, because some of them you can resolve individually, right? So as soon as you start resolving individually, what you are left, right, may not be perfectly stochastic anymore, because if you subtract too many, what you're left is not stochastic. But ignoring that problem, this is roughly what you expect. And now the amplitude depends on how many black holes we think we have in the universe, right? At the moment, there's still an error band on that. But these are the guys we measure in LIGO, right? So our knowledge of these guys is increasing by the month, right? So hopefully by the time that LISA flies, at least, I mean, then there's of course an assumption of redshift, right? Because LISA can measure out to much deeper in redshift than LIGO can, right? So you take the measurement of LIGO, you have to make some assumption, some modeling on the redshift dependence, and then you get this curve with astro error bars. Yeah. Yeah, yeah. I mean, they come with error bars, right? I mean, you know, yeah, they come with error bars, right? I mean, in these models. I mean, in these models you put some physics, right? You put some effective parameters, you fit to the data. You get models, the different groups of different models, right? I don't think there's a huge disagreement between them, but of course there are error bars, right? Because you're not modeling this from first principles. You're not starting from CMB, right, and modeling all the way to galaxy population.
If there are no other questions, let's